and you want to eat, what do? You just do you see? And so when you apply an external force to cause the movement of heat from one point to the other, is what we say the forced convection. So the other type of convection is what we say the forced convection. Forced convection. Let's discuss about the forced convection now. Forced convection. So now actually about the forced convection. So about the forced convection. This is by the which is the what the criteria of classifying this. This is external force, or blower, or a fan. A good example is like you are using a fan to cool your body, cooling the body by using a fan. You have your fan of fan. Example is cooling a body using a fan. Or for example in the experiments, one from 6, you just go this week I just teach about the experiments. I'll just tell you to make sure you cool your liquid by just stirring it. So you just force it to cool. You just say, for example, cooling by using a fan, cooling your food by blowing air on a hot food. That's forced convection. So you force your food to cool. That's what we say the forced convection. That's another type. Let's talk about the laws, man. Let's talk about the laws. The third thing that I'm going to discuss with you is about the laws. If you don't have my books, make sure you download. You just go and DM me on WhatsApp and take the books for hits. That's good books. They have a lot of solved questions and some criteria on how to do physics. Hey, gang, if you don't have my books, make sure you DM me on those numbers on WhatsApp and take you a book. There are my numbers down there. See you. And let's talk about the laws. Talk about the laws. We have the two laws actually governing the convection. So the convection doesn't occur just without the laws. Actually it occurs under some principles. So scientists sat down and did some experiments, and observers intend a real pattern that always operates in all forms of convection. And there are two laws. One of the laws is what we call the Newton's law of cooling, and the second thing is about the Pettit and Durant law. Let's talk about the laws. Let's talk about the laws of convection. Laws of convection. Laws of convection. Let's talk about the laws of convection. One is Newton's law of cooling. Newton's law of cooling. And the second thing is about what we say the Pettit and Durant law. Pettit and the Durant law. So talk about the Newton's law of cooling. What does it state? So the Newton's law of cooling actually states this one is the modification of this one. The Pettit and Durant law is the modification of Newton's law of cooling. But they are the same law. But to some limitations, it doesn't work. Let's discuss about the Newton's law. You just see about it. So talking about the Newton's law, Newton's law of cooling. Cooling, it states that the rate of cooling of the body is in proportion to its excess temperature from the surrounding. If this object is 100 degrees centigrade and the environment is 25, so the excess temperature is the temperature that has exceeded from that of the environment. So the excess temperature will just be 75. Do you get me? And so the rate of cooling of this object will just depend on how much it has exceeded from the environment temperature. That's what we say the rate of cooling is then proportional to its excess temperature to the surrounding. So if you have a hot object, it will cool faster than the cold object or than the normal temperature object. Why? Because it's a law. The rate of cooling is then proportional to its excess temperature to the surrounding. So the rate of cooling, cooling is proportional, directly proportional, is directly proportional to the excessive temperature to the surrounding, that is of the surrounding. So when talking about this, we say the rate of cooling is the heat lost per time is directly proportional to what we say the temperature of the object minus the temperature of the surrounding. That's what Newton says, i.e. mathematical. But we say we can make the analysis of this. Hey, from 6 now, pay attention here, because this law is what we use in the theories of the experiments. So we make analysis, mathematical analysis of Newton's law. Hey, look here. Look here. If you have a sentient liquid here, the heat it can lose or absorb depends on its specific heat capacity. Heat will just be mc, the change of its temperature. So if we find the rate of losing here, we divide by time, but heat loss is this one. So actually, if this is the heat lost, it's just equal to rate of losing heat is just equal to mc, the change in temperature per change in time. So if we have the change in heat lost, the change, the differential for is just equal now to what we say the rate of losing as per newtons. So here we put the constant K, but the excess temperature, theta minus that excess temperature is from Newton's law of cooling. Do you see it? Yeah. So from there, I can now say some issues that I can combine the like terms to the like terms so as I may integrate the values. But you see, if I make K over MC, So if I say K over MC, K over MC here, but times dt, but the like temperature and temperature, let me correct them, temperature and the change of the excess temperature here. What is this? If I integrate this value, keep in mind this, the rate of cooling, so the heat continues to increase as per time. So the heat continues to increase as per time. You see? So this K over MC, let me make another constant here, lambda. But you know in your mind, this lambda is the specific, is the thermoconductivity, the constant here from the Newton's law, and we have the mass and the specific heat capacity. So we say, talking about this lambda here, I just say d theta over what we say theta minus that of the surrounding is just equal to lambda but to dt, negative. Do you see? So when I integrate the time, when I integrate the temperature from a certain limit I've just been given, from where I will start to where I will end, I just get now after that integration, hey, if you haven't started about what we say the integration or differentiation, go to start them before coming here. So we just say, I just do it in here, Newton's law of cooling now, rate of cooling, so what I just say here, okay, so I can say here, if I integrate this, I just get ln of who, theta minus that of the surrounding, then I get what is equal to negative lambda t. So what is going on here, but plus what we say the constant, because I have no limits on my integration. So what is this? Constant. You can just obtain the constant initially, as you know. So we just say at t, what we say time is just equal to 0. What is this now? If this is 0, then A will just be equal to this, but at the temperature which is now theta equal to 0. Meaning at theta is just equal to theta naught, meaning at 0 new centigrade. 0 new centigrade. So at this, the initial value, at times as 0, the temperature is just the equal to initial value. Now A will just be A. If I put this equal to, so let me substitute the values actually. Let me substitute the values. If I say ln of this initial was theta naught, that is for initial temperature minus the surrounding is just equal to, what is this? Negative, but this is 0 T, then I plus A. So if A, I can just get A is equal to what I say, ln of theta 0 plus that of, minus that of the surrounding, minus that of the surrounding here. So I can come and substitute this value here to get at time t, at the theta, at the certain theta. So ln of a certain temperature and that of the surrounding actually is just equal to negative of what I say, this times t, but what is A here is ln of theta naught minus what we say, that of the surrounding. You see? So getting this actually here, this lambda per t is just equal, this comes here to be minus here. So Lm, and this is that of Q minus that of the surrounding, but minus what we say, the ln of theta naught minus that of the surrounding. So actually talking about this ln, or just have talking about the F, theta minus that of the surrounding, about that of the initial temperature minus that of the surrounding, is just equal to negative what we say, negative lambda t. So you can just write, because just for the principle for logarithm, I just write them now. Hey, woo, sad. Oh yeah, so I just write it here. So let me make it clear here. Let me make it clear here. I came to write it here, so I just write that. I just say ln of what we say, theta minus that of the surrounding chief over Q naught minus that of the surrounding, and then we have what we say. So this ln comes and lies here as L light of lambda t. You see? So getting the temperature theta for that time t, we just say is equal to this times this, and this comes here to be plus the surrounding, so we plus what we say, Q naught of that of the surrounding, the difference, the excess temperature initially, times E, but negative T minus T. So on forging, on your experiments here, you just use this principle. You just use this principle here. So you just determine firstly the excess temperature. The initial excess temperature is the one that you just use in your forging for a given time and for a given temperature. So you just be given depending on the table, either the temperature or to find the time. So you find the time, or so you forge it to just save time in your experiment. That's all about the forging. I'll just discuss it with you this week on this experiments for heat. Let's go direct to the applications, man. Let's talk about the applications for heat. Applications now. Let's talk about the applications. 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 Let's talk about the applications. Let's talk about the applications. So how about applications? Actually, when I'm talking about the applications now, when I'm just speaking about the applications, there are more applications of convection in this life. But I talk about only four applications of convection here. So as I motivate you to go and start about, in my books there are many applications there, so you go and read them. Let's talk about, very important is about the land breeze and sea breeze. What about the land breeze and sea breeze? Land breeze applications now. Applications of what we say the convection. Okay, let's talk about one is about land breeze. And what we say the sea breeze. Hey, land breeze and sea breeze. Land breeze and sea breeze. Land breeze and sea breeze. So talking actually about the land breeze and sea breeze, look here. If you have this is the land, man, land, chief, and here this is the sea. So the sea contains some water here, like this, water. So actually, during the day, chief, during the day, here we have a sun, sun like that, emitting some radiations toward the earth. So the land, since contains sand, it have sand. Sand is more conductive than what? Because sand tends to contain some metals here. So since it contains sand, the land is more hot, more hot during the day. You see, being hot and here being less hot than here. It's not it's too cold. It's also receiving the radiations, but here receives more radiations than here. What happens here? Some lights are being reflected than being absorbed than here. So here, actually, during the day now, when you are explaining about the land breeze and sea breeze, you just say for a land breeze now, which occurs during the day, land breeze. Land breeze tends to occur, we say the land breeze and sea breeze tends to occur during the day. The sea breeze, upepo wa bahari, tends to occur during the day. So what happens here? The land is more hot, so the air above it is more hot. So the air becomes hot. So if it becomes hot, the air here, as it's hot, rises because it becomes less denser. As it rises up during the day, this cold one, less hot, comes to replace this here, air. Air above water is less hot. Less hot comes to replace this one. So air which has just rises, as this comes to replace this one, this air falls down, the cold one. Falls to replace this one. As it falls to replace this one goes to replace this one. So the convectional movement of air is what causes what we say there.